So now we are going to learn about EM algorithm, and if you can recall from the lecture, EM algorithms are mainly used when we have missing data and we want to estimate the parameters of the distribution, and we saw the examples for normal and binomial distribution. So we are going to reconsider them over here also, and we will begin with your normal one, EM algorithm for normal. Okay, so first of all we will import numpy as np, and let us take whatever is the given data to us. So let me just mention x observed, these are the observed values. So we are going to create an array for this, np.array. It would contain observed data points. So those are 0.55, 2.20, 1.37, 0.85, 0.92 and 2.57. So you can see that these are the same data points that we considered in your theory part also. So 6 data points are given. Okay, and these are the observed ones. So how many are observed? So let us store this in n observed, number of observed data points. It would be the length of this particular array. Okay, and what are the total numbers? Let me just write, n total is 10. That is the total number of data points. It means 4 are missing in this case, and you can write as n missing would be n total minus n observed. Okay, so from the total, that is 10, you will subtract the observed, that is 6, you will get 4. Now let us, to begin with, let us take the initial values of the parameters. So let us take as mu old as 0.8 and sigma square old, sigma 2 old as 1. Okay, now we are going to define a function for the E step, and likewise we will do for the maximization step. Okay, so in E step, basically it will calculate the expected log likelihood of the observed data points given the current values of mu and sigma square that we have taken, 0.8 and 1. So let us define that function. So let me define a function for the E step. So define E step, and here you will enter mu and sigma square. So mu sigma square, so it would be returning minus n observed. If you can recall this, the form that we wrote in while we are calculating the estimator for normal distribution. So we wrote this into np dot log of sigma square, okay, minus 0.5 divided by sigma square into np dot sum x observed, summation xi square, so you will raise it to the power 2, okay, plus, okay, so minus 0.5 by, so 1 by 2 sigma square into summation xi square plus mu divided by sigma square into np dot sum, again summation xi would come, x observed minus, there was n total number of observations, into mu square divided by 2 sigma square. 2 sigma square. So 2 sigma square would be in bracket over here. Okay, so let us just cross check. So minus n observed divided by twice of sigma square, log sigma square, and then it would be sigma square times summation xi square, then mu by sigma square into summation xi minus n mu square divided by 2 sigma square. So this code over here, it is defining your E step. Okay, E step function. It will compute the expected value of the complete data log likelihood, and this function would take the current parameter estimates for mu and sigma square as input, and it will return the expected log likelihood. Likewise, we can define a function for the m step. Define a function for the m step in order to update your mu and sigma square. So define m underscore step. So here it would be mu old comma sigma square old okay. So here your mu new, if you remember, we obtain mu new as summation xi plus n times mu divided by the total number of observations. So let me just write np dot sum, because we are finding out this, we are using this function over here, x observed summation xi x observed plus n underscore missing, that is n minus m term that we had, into mu old, and this whole is divided by n total. Okay, so we can cross check. np dot sum x observed would be there plus n minus m times mu old divided by n total. Likewise, we can also write for sigma square new. This one would be what? Again, np dot sum x summation xi square basically. So x observed square, okay, plus n missing, that is n minus m times sigma square old. So sigma square old plus mu old raised to the power 2 whole divided by total number of observations minus mu new whole square. So mu new that we have just calculated above, right? If you remember, this is the formula that we had for your mu and sigma square. So np dot sum x observed, this entire thing would be there. So this bracket will not end over here, rather it would end at this point. Okay, divided by n total minus mu new, and then it would return mu new and sigma square new. Okay, so we have defined an m step function also that is going to update the parameter estimates mu and sigma square based on the expected log likelihood. Okay, now for your EM algorithm, we are considering a tolerance level and convergence tolerance basically, and your maximum number of iterations that we will be needing. So here I can write here itself. So tolerance as 1e minus 6. Okay, so this algorithm basically checks for convergence by comparing the absolute differences between the old and the new estimates. Okay, so if both the differences are smaller than the specified tolerance that we have defined just now, then the algorithm has converged and it will exit the loop. So for that purpose, we are writing it. And how many iterations it will go? So let me just write that. Maximum iterations, suppose, is 100 for our case. Now let us initiate the for loop for iteration in range, that is the maximum number of iterations that we have defined. Okay, so this is a for loop that iterates for a maximum of these many number of iterations. It will control the number of times the EM algorithm's E step and M step would be performed or executed. For this, we would write mu nu would be there, sigma square nu, so then M step, mu old, sigma square old. Okay, so inside the loop, the M step is called with the current parameters estimates, that is mu old and sigma square old, which are used to update the parameter estimates over here as mu nu and this. Now the updated parameter estimates are stored in mu nu and sigma square nu. Okay. Next, what we do is we start this if statement. So if we write if np dot absolute, the difference that we were checking, if np dot absolute mu nu minus mu old, right, the difference between these two is less than the tolerance, okay, and np dot absolute of sigma square nu, and difference between sigma square nu and sigma square old, if this is less than the tolerance, both the differences are less than the tolerance, then the algorithm has converged and it will exit the loop. For this, what we do is we write break. Okay, otherwise what will happen? Mu old and sigma square old would be storing mu nu and sigma square nu. Okay, so if the algorithm has not converged, the updated estimates, that is mu nu and sigma square nu, become the new estimates for the next iteration. Okay, it will again go to this and it will again start. Okay, so this loop is basically a major part of your EM algorithm because it will iterate through your E step and the M step repeatedly, updating the parameters estimates until the convergence criteria is met or the maximum number of iterations is reached. Okay, so finally we can print your MLE for mu nu and mu old. So maybe just I could, okay, so I'll write the comment over here, print maximum likelihood estimator of mu would be mu nu and let us write the estimate for your sigma MLE of sigma square would be sigma square nu. Okay, so this is what you get over here. So your MLE maximum likelihood estimate for mu is 1.40 and for sigma square it comes out as 0.544. Okay, so you started with 0.8 mu and it reached till 1.4, and for sigma square old it is 0.544. Okay, so you see that even though your data was missing, you were able to find out an estimate for these parameters by using the EM algorithm, and that is why this is a very important algorithm and concept. So likewise, this is for normal distribution, because these are the simple cases. You can generalize it for multivariate normal distribution, likewise for multinomial distribution, so that those things can also be performed using the EM algorithm. Next, we are going to do it for binomial distribution. So let us do that. So here again we are going to import NumPy. Although we have imported it, you do not have to write it again and again, but if it is, you need to rerun this step in case. So I'm just writing it afresh. So you will write the given data. So let us just write what are the observed values. So for that we are going to create an array, np.array, and here we would write 2, 4, 2, 1, 3, 5, 3, 2. 2, 4, 2, 1, 3, 5, 3, 2. Okay. K is 5, that is the number of trials in the binomial distribution, and your n observed would be the same as the length of this x observed. Okay. And what are the total number of observations? And total would be 12 in our case, total number of data points. And n missing, let us write, n missing would be the difference between the total number of observations minus the observed data points, number of observed data points. Okay, so these are the given data point. This is given to us. Now we are going to take or initiate a value. So let us assume that p old is 0.3. Let us start with this. It can vary from 0 to 1, so I'm just picking up 0.3. Now we are going to define e step and function for e and m step. Define a function for e step. So define e step over here. So in e step you will have p and x observed and k, because n, p and k would be there. So it would return np.sum summation xi, and here we would have np.log np.array, bracket we would write p raised to the power xi into, sorry, xi, it would be xi into 1 minus p times k minus xi for xi in x observed. Okay, so this is your e step. So same thing that we have obtained in the lecture, same I have written over here, p raised to power xi and 1 minus p raised, sorry, here it would be double star, because p raised to power xi into 1 minus p raised to power k minus xi, for xi is taking value in this x observed. Likewise, we are going to define a function for your m step. Define a function for m step. So define m step. So here we would write p old, x observed and n missing. what will be P new in this case? P new would be NP dot sum X observed. Okay, within this only, NP dot sum observed. The missing, that is n minus m times K and K into P old whole divided by Nk, that is n total, into K, and finally this would return your P new. Okay, so we have defined these two. Then we would set the tolerance level, so we can use the same tolerance and the maximum number of iterations from here. Can copy this from here. Okay, so tolerance is this for iteration in range max iterations. Okay, now we are initiating a for loop. In this case, P new would be m step, whatever is calculated from here, m step P old X observed K and missing. So it would be assigned to P new. Okay, and if the absolute value from here, we are going to use from NumPy this function abs absolute value, that is the difference between the P new minus P old. If this is less than your tolerance, okay, in that case we will break and we will come outside the loop. Otherwise, P old would be assigned as P new and the loop will continue. Okay, now you can print the MLE, print MLE of P would be P underscore new. P old, sorry, here K is missing in this step. So let me rerun this. Sorry, comma. Yeah, so MLE is 0.549. Okay, so you have simply, first of all, you have imported NumPy and then you have written what is given to you as the data set, and you have written how many observations are missing. Then you have initiated a value for P, that is estimator, and you have defined the functions for your E and M step that we have already studied in the theory. And those same steps we are writing, we are just writing in terms of Python. And then finally we have written this P new we have obtained, and then before initiating a for loop, we define this tolerance level and maximum number of iterations, and for each iteration it will go through this M step, and whatever is there it will assign this to P new, and now it will calculate the absolute difference between your P new and P old, and if it comes out less than the tolerance level, it would break. Otherwise it will be again assigned as P old and the process will continue. Okay, and we saw that after doing this we obtain the MLE of P as 0.54 or 0.55. Okay, so in these two cases we had a data set, small data set, and then we were working with that in order to find the MLEs. Similarly, if you have a synthetic data set also, then also you can basically generate a data and then you can find the estimate. Okay, so for that let us consider a small example from binomial case. So EM algorithm, so just let me write synthetic binomial. So some of the steps would be just same, so let me just, or I would write it. Okay, so we are going to import NumPy as NP. Next, np.random.seed. So we are familiar with these terms over here. 123. Now we are going to set the true parameter, true p, as suppose 0.6. Okay, and the total number of data points that we have is suppose 50. You can generate synthetic data from a binomial. So let me just write synthetic np.random.binomial. So from binomial we are going to generate. So np is 5, n is 5, and then you are going to have true p, true underscore p, and n total over here. Okay. So np.random.binomial, and now you are going to split your data into observed and missing parts. Okay, so n observed is 30. Okay, so 30 observations are, you are having 30 observations out of 50, and x observed, let us take from the synthetic data that you have generated, from that data n observed. Okay, so out of this data set 30 would be taken out, and n missing would now be your n total, that is 50 minus observed, that is 30. So 50 minus 30 would be 20. 20 are missing. Let us initiate a p-value. So let me just, initial p is suppose 0.3. Now we need to again define an E step and M step. So probably we could just simply copy it from here. We can use the same thing. So let me just copy it from here and see if it is correct. So define your E step first of all. So P x observed k. So return np.sum, np.log, np.array. These things would be same. And now you will define a function for the M step to update your P. So P new, X observed and missing. So everything is same in this case. Now tolerance and max number of iterations. For iteration in range, P new would be M step. Same thing. So estimated P new minus estimated P if difference between these two is less than the tolerance, then it would break. Then estimated P, same as P new, and if we print estimated P, let me just write this finally, 0.5933. okay, this is what you get, and you generated this data from binomial with parameter P was in this case you initiated it with 0.3, okay, and the true P that you took was 0.6. You can see that it is very close to it because you generated a sample from binomial with parameter 0.6, and now what you are getting, the estimated value is 0.5933. Although there are 20 observations which are missing. Okay, so this way also you can go ahead with your EM algorithm. So you just have to be familiar with how you are defining your functions and how your iteration is going to take place. Now this tolerance level can also be varied based upon your objective, and then same steps would be performed. So this basically completes your week 7, that was on unbiased estimation and EM algorithm.